Welcome to our comprehensive guide on writing optimized code for embedded systems. In this video, we'll explore the essential rules every engineer should follow to ensure their embedded software is efficient, reliable, and maintainable. Whether you're working with microcontrollers in automotive, IoT, or industrial automation, these principles will help you get the most out of your hardware. Let's dive in and discover how to balance performance, memory usage, and deterministic behavior in your next embedded project. Optimizing code for embedded systems isn't just about making things run faster. It's about understanding the unique constraints of embedded hardware, limited RAM, strict timing, and the need for predictable, safe operation. Unlike desktop or cloud software, embedded applications often run in environments where reliability and efficiency are critical. By following a disciplined set of practices, engineers can create firmware that's not only high-performing but also robust and maintainable. Before we jump into the details, here's a quick overview of what we'll cover. We'll start with choosing the right algorithm, then move through topics like data types, memory management, interrupt routines, and hardware acceleration. Each rule is supported by practical examples so you can see how these concepts apply in real-world embedded development. Let's get started with the first rule. Rule number 1, always choose the right algorithm first. Algorithmic efficiency can provide the biggest performance gains in your code. For example, replacing a simple O and 2 loop with an O and log n algorithm can make a dramatic difference, often more than any micro-optimization. Instead of scanning arrays repeatedly, consider using binary search, lookup tables, or incremental updates. The right algorithm sets the foundation for all other optimization. See algorithm efficiency in action. Imagine you need to search for a value in a sorted array. Instead of a linear search, a binary search can cut down the number of comparisons dramatically. Similarly, using lookup tables for frequently accessed data can save both time and processing power. Always analyze your problem and select the most efficient algorithm before worrying about low-level code tweaks. Rule 2 is about data precision. Always use correctly sized fixed-width integer types. In embedded systems, using types like uint8t, uint16t, and uint32t helps prevent ambiguity, minimizes memory usage, and improves portability. These types ensure your arithmetic is correct and predictable across different platforms. Avoid generic int or long types unless you're certain of their size on your target hardware. Using fixed-width types isn't just about saving memory. It also makes your code more portable and less error-prone. For example, if you use uint8t for a value that never exceeds 255, you guarantee that your code will behave the same way on any microcontroller, regardless of architecture. This consistency is key for reliable embedded firmware. Rule 3, avoid floating-point operations in critical code paths. Most microcontrollers lack dedicated floating-point units, making floating-point math slow and code-heavy. Instead, use fixed-point arithmetic whenever possible. Fixed-point math is not only faster and smaller, but it also ensures deterministic execution, crucial for real-time embedded systems. Let's look at an example. Suppose you need to perform calculations on sensor data. Instead of using floating-point variables, scale your values and use integers to represent fixed-point numbers. This approach keeps your code fast and predictable, especially on hardware without floating-point support. It's a simple change that can have a big impact on performance. Rule 4 is all about memory management. Minimize or eliminate dynamic memory allocation. Dynamic memory can cause fragmentation, unpredictability, and system instability, especially in long-running embedded applications. Instead, prefer static allocation and fixed-size buffers. This approach makes your code more robust and easier to debug. By using static allocation, you know exactly how much memory your program will use at compile time. This predictability is essential for embedded systems where resources are limited and reliability is paramount. Fixed-size buffers also make it easier to catch bugs and prevent memory leaks. Rule 5, keep interrupt service routines or ISRs short and deterministic. ISRs should execute quickly to reduce system latency and jitter. The best practice is to set flags, push data into FIFO buffers, and defer heavy processing to the main loop. This keeps your system responsive and avoids blocking other critical interrupts. In writing ISRs, avoid lengthy computations or blocking calls. Instead, use them to signal the main application that work needs to be done. For example, an ISR might read a sensor value and store it in a buffer, then set a flag for the main loop to process the data. This approach ensures your system remains responsive and predictable. Rule 6, use the const keyword to store read-only data in flash or ROM, not RAM. Constants like lookup tables and configuration arrays shouldn't occupy precious RAM. By marking them as const, you allow the linker to place them in non-volatile memory, freeing up RAM for variables that actually need to change. Storing read-only data in flash or ROM not only saves RAM but also protects your data from accidental modification. This is especially important for configuration settings and calibration tables that must remain unchanged during operation. It's a simple habit that pays off in system stability. Rule 7, use bitwise operations and pack multiple flags into a single byte or word. Instead of using separate Boolean variables, you can represent multiple states with just a few bits. This technique saves memory and can speed up your code, especially in resource-constrained environments. For example, you might use a single byte to store the status of 8 different features, with each bit representing a different flag. Bitwise operations like AND, OR, and XOR make it easy to set, clear, or check these flags. This approach is both memory efficient and fast, making it ideal for embedded systems. Rule 8. Eliminate busy waiting by using interrupts or RTOS synchronization mechanisms. Busy loops waste CPU cycles and power, especially in battery-powered devices. Instead, use interrupts, semaphores, or event flags to signal when work needs to be done. This approach keeps your system efficient and responsive. Interrupts allow your system to react immediately to external events without wasting time in busy loops. In more complex systems, an RTOS can provide semaphores and event flags for efficient task synchronization. These mechanisms help you build low-power, high-performance embedded applications. Rule 9. Leverage your compiler's optimization features and use inline functions wisely. Modern compilers can optimize code aggressively when given the right flags, such as O2 or keep your functions small and only use inline where it truly improves performance. Overusing inline can actually increase code size and reduce efficiency. To get the most from your compiler, use the appropriate optimization level for your project. Test your code with different settings to find the best balance between speed and size. Remember, not every function benefits from being inlined. Reserve this for small, frequently called routines where the overhead of a function call is significant. Rule 10. Reduce memory accesses and avoid redundant computations. Accessing RAM is often slower than performing arithmetic operations. Cache values locally in registers or stack variables and avoid recalculating the same expression multiple times. This can make your code both faster and more energy efficient. For example, if you need to use the result of a calculation several times, store it in a local variable instead of recomputing it. This reduces memory traffic and can significantly speed up your code, especially in tight loops or real-time routines. Always look for opportunities to minimize unnecessary memory accesses. Rule 11. Use hardware acceleration instead of bit banging. Most modern microcontrollers include peripherals like DMA, timers, and hardware UART SPI I2C modules. These features can dramatically reduce CPU load and improve performance. Let the hardware do the heavy lifting whenever possible. Bit banging, manually toggling pins in software, can be useful for simple tasks, but it's inefficient for high-speed or complex protocols. Whenever possible, use your microcontroller's built-in peripherals. This not only saves CPU cycles but also ensures more reliable and consistent timing. Let's recap the essential rules for writing optimized embedded code. Choose the right algorithm, use fixed-width types, avoid floating point in critical paths, minimize dynamic memory, keep ISRs short, store constants in flash, use bitwise operations, eliminate busy waiting, leverage compiler optimization, reduce memory accesses, and use hardware acceleration. These practices form the foundation of efficient embedded firmware. Optimizing embedded code isn't about clever tricks, it's about engineering discipline and hardware awareness. By consistently applying these rules, you'll create firmware that's faster, smaller, more reliable, and more energy efficient. This disciplined approach is what separates good embedded engineers from great ones. As embedded systems become more complex, the need for optimized, maintainable code only grows. From automotive control units to IoT devices and industrial automation, efficient firmware is the key to unlocking the full potential of your hardware. Mastering these principles will help you deliver robust, real-world performance in any embedded application. Let's take a closer look at algorithm selection. When optimizing embedded code, always start by analyzing the problem and considering the most efficient algorithm. For example, sorting algorithms like quicksort or mergesort can be much faster than bubble sort for large datasets. The right choice can save both time and energy, especially in resource-constrained environments. Using fixed-width integer types not only saves memory but also ensures your code is portable across different platforms. This is especially important when your firmware needs to run on multiple microcontroller families. By standardizing on types like UINT8T and UINT16T, you avoid surprises and make your code easier to maintain. In floating point math is unavoidable. Consider using libraries or hardware support if available. However, for most embedded applications, fixed-point arithmetic is sufficient and much more efficient. Learn to scale your values and work with integers to achieve the precision you need without the overhead of floating-point operations. Effective memory management is crucial in embedded systems. By avoiding dynamic allocation and using static buffers, you reduce the risk of fragmentation and unpredictable behavior. Always plan your memory usage ahead of time and allocate only what you need. This approach leads to more stable and reliable firmware. Interrupts are a powerful tool in embedded systems, but they must be used carefully. Keep your ISRs as short as possible and avoid blocking operations. Use them to signal the main application or move data into buffers, then let the main loop handle the heavy lifting. This keeps your system responsive and avoids missed events. By marking lookup tables and configuration arrays as const, you ensure they are stored in flash or ROM instead of RAM. This not only saves valuable RAM but also protects your data from accidental modification. It's a best practice that every embedded engineer should adopt. Bitwise operations are essential for efficient embedded programming. By packing multiple flags into a single byte or word, you save memory and make your code more efficient. Learn to use bitwise and/or and XOR to manipulate these flags quickly and safely. Polling loops can waste CPU time and drain battery life. Instead, use interrupts to respond to events as they happen. In more complex systems, RTOS mechanisms like semaphores and event flags provide efficient task synchronization without busy waiting. Experiment with different compiler optimization levels to find the best balance for your project. Higher optimization can improve speed or reduce code size, but always test thoroughly to ensure your code still behaves as expected. Use inline functions sparingly and only where they provide a real benefit. Avoid recalculating the same value multiple times. Store results in local variables and reuse them as needed. This reduces memory traffic and can significantly speed up your code, especially in performance-critical sections. Take advantage of your microcontroller's hardware features. Use DMA for data transfers, hardware timers for precise timing, and built-in communication modules for serial protocols. Offloading these tasks to hardware frees up the CPU for other work and improves overall system performance. Bit banging can be useful for simple or low-speed tasks, but it's not suitable for high-speed or complex protocols. Whenever possible, use your microcontroller's hardware peripherals for communication and timing. This ensures more reliable operation and frees up CPU resources. The key to successful embedded development is consistency. Apply these optimization rules throughout your codebase, not just in performance-critical sections. Consistent practices make your code easier to maintain, debug, and extend as your project grows. While optimization is important, never sacrifice maintainability for a small performance gain. Write clear, well-documented code and use optimization techniques that don't obscure your logic. The best embedded code is both efficient and easy to understand. Understanding your hardware is just as important as writing good code. Learn the capabilities and limitations of your microcontroller and tailor your optimizations to fit. This hardware awareness allows you to fully exploit the features of your platform and avoid common pitfalls. As embedded systems evolve, they become more complex and interconnected. By mastering these optimization rules now, you'll be prepared to tackle larger, more demanding projects in the future. The skills you develop today will serve you well as technology advances. Thank you for joining us on this journey through the essential rules for writing optimized embedded code. By applying these principles, you'll create firmware that's efficient, reliable, and ready for the challenges of modern embedded systems. Keep exploring, keep learning, and continue to refine your skills as an embedded engineer.